In 1985, aboard the Soviet space station Salyut 7, a cosmonaut was unpacking supplies in microgravity when a standard wing nut slipped off its threaded rod. It rotated smoothly for several seconds, suddenly snapped 180 degrees, and kept right on spinning. That cosmonaut was Vladimir Dzhanibekov, and his chance observation of this hardware tumbling in orbit brought a bizarre rotational quirk into the modern scientific spotlight. Under the basic laws of classical physics, an object in motion maintains its orientation unless an outside force or torque acts upon it. Yet this small piece of metal appeared to be turning itself over using nothing but its own momentum. You do not need to be in zero gravity to witness this happen. Physicists refer to this exact behavior as the Tennis Racket Theorem. Toss a standard tennis racket into the air, spinning it strictly along its handle axis, and it will tumble chaotically mid-flight before you catch it. To understand how an object can spontaneously reverse its orientation entirely on its own, we have to look past the surface and examine a geometric trap hidden inside every three-dimensional object. This animated diagram uses a simplified rigid block to visualize Euler's equations of motion. Every solid object has three principal axes of rotation, intersecting at its center of mass. Each axis is defined by a principal moment of inertia. We define the first axis as the one with the maximum moment, meaning the mass is spread furthest from the center of rotation. Spinning an object along this wide, short dimension is highly stable. It actively resists forces trying to knock it off its path. The second axis sits at the opposite extreme, featuring the minimum moment of inertia. Rotation along this longest, thinnest dimension is also perfectly stable. Watching an object spin smoothly along either of these paths creates a false sense of security. It tricks our intuition into believing that all rotational motion in three dimensions remains orderly and predictable. The anomaly lives in the third path, the intermediate axis. Spinning an object along its middle dimension is the direct mechanical trigger for the Dzhanibekov Effect. This graph visualizes the math using a saddle point. Notice how the surface curves upward in one direction and downward in another, leaving our particle resting in the exact dead center. That center point is an unstable equilibrium. If the object receives a microscopic nudge, the curve amplifies that vibration, accelerating the motion away from the center. As this instability grows, the object flips to redistribute its rotational kinetic energy, all while keeping its total angular momentum strictly conserved. This 180-degree flip is the only way for the object to satisfy its own conservation laws. Because the energy cannot dissipate, the rotation is forced to follow a looping path through space until it reaches the opposite orientation. This geometric trap scales up far beyond handheld tools. Spacecraft possess their own unique principal axes, determined by the specific placement of heavy fuel tanks, instruments, and solar panels. In the vacuum of orbit, there is zero air resistance or friction to dampen a slight wobble, making the intermediate axis exceptionally dangerous. If a satellite begins rotating along its middle axis, tiny vibrations amplify until the entire craft suddenly and violently tumbles out of alignment. To prevent this, aerospace engineers calculate the specific moments of inertia for every payload before launch. They must ensure the mass is distributed so the planned spin never encounters this intermediate axis. The same physics that causes a tennis racket to tumble also determines the stability of every satellite in orbit. If engineers miscalculate the mass distribution, a billion-dollar instrument can become an unrecoverable, tumbling wreck. Euler's equations of motion represent highly rigid, deterministic mathematical laws governing how objects move through space. Yet when we apply those rigid equations to the intermediate axis, they produce a physical reality defined by chaotic, flipping motion. Classical mechanics rarely behaves like a perfectly predictable ticking clock. In the right geometric conditions, strictly deterministic rules inherently breed spontaneous, surprising complexity.